Have you ever stared at a math problem that just looked completely, utterly impossible, like a riddle with no answer? Well, today we're diving headfirst into one of those. And trust me, by the time we're done, we're going to crack it wide open. So, meet our villain for today, a monstrous 15th degree polynomial. I mean, just look at that thing, with all those giant numbers and terms stretching on and on. Trying to find the exact value for x feels like a fool's errand. This is the kind of equation that can make even powerful computers sweat. And that really leads us to the core mystery here. Is it possible that buried inside all of that mess, there's an answer that's actually simple? Or are we stuck with just getting kind of close to the real solution? That is the big question we're going to tackle. But before we can find that beautifully simple solution, we gotta talk about why the old school methods, the ones mathematicians have used for ages, just fall flat when they come up against a beast like this one. Here's a good way to think about it. The traditional methods on the left, they're kind of like taking a blurry photo of the answer. Yeah, you can make out the general shape, but all the important details are lost to tiny rounding errors. But a symbolic solution on the right, that's a crystal clear 4K picture. It's the exact value, perfect, down to the last detail. And that's really the heart of the problem. When you have an equation this big, those little approximation errors start to add up, they snowball, and pretty soon your final answer is way off. It's just not reliable. We need a different tool for the job. And that brings us to the hero of our story, a totally different way of thinking about the problem called Ezouidi's theorem. So what is this theorem, really? Well, you can think of it like a master key. Instead of just guessing and checking and getting close, it follows a very clever step-by-step process to find the exact symbolic roots. It's designed to solve the very problems that old-school algebra just gave up on. All right, so now we get to see this theorem in action. And don't you worry, we are not about to get bogged down in a bunch of terrifying formulas. We're just going to focus on the results, which honestly are pretty mind-blowing. Okay, so the first step is to reframe our polynomial a little bit. See these S terms? Instead of the big numbers, we have these symbols. Think of them as placeholders or secret ingredients. The whole point of the theorem is to figure out the exact value of every single one of these, from S0 all the way to S14. And the way it finds them is recursive. Now, that sounds fancy, but all it really means is that each step builds on the one before it. You find the first answer, S0, then you use that result to help find the next one, S1, and so on and so on. It's like a chain reaction of logic. So after all that, what does the theorem's complex calculation spit out for that very first symbolic coefficient, S0? The answer is 0. A nice, simple, clean 0. Okay, interesting. But this is where things start to get a little weird. What about the next one, S1? The theorem calculates that, and guess what? It's also 0. And the next one after that, stick 2? You guessed it, 0 again. You see the pattern here? This isn't just a coincidence. The theorem is uncovering something deep and simple, hidden inside the complexity. And this pattern just keeps going. One after another, the process reveals that every single one of these symbolic coefficients is exactly, precisely 0. The whole thing, from start to finish, all those complicated building blocks were nothing all along. So now we get to the big payoff, the final aha moment. What on earth happens when we take this incredible result and plug it back into our equation? So remember this setup? Our entire polynomial was built on these S coefficients that we just spent all this time finding. What happens to the equation when every single one of them is actually 0? Well, every one of those complicated terms just disappears. 0 times x to the 14th, that's 0. 0 times x to the 13th, also 0. All the way down the line, the complexity just gets wiped out. It all just vanishes. And this is what we're left with. Our terrifying monster polynomial was just a mask for this stunningly simple little equation, x to the power of 15 equals 0. I mean, the difference is just amazing. And the solution from here is, well, it's obvious, right? X has to be 0. The fancy term multiplicity 15 is just the formal way of saying that because the original equation was to the 15th power, we count that root of 0 15 times. An unbelievably elegant answer that was hiding there the whole time. And this really brings it all home. The reason we can be so confident in this answer is because every single step was purely symbolic. There was no rounding, no estimating, This means we know for a fact that x equals 0 is the one perfect, error-free solution. No blurry photos, just the truth.
Going through this whole process really makes you wonder, doesn't it? It proves that sometimes the most intimidating, complicated-looking problems out there are really just simple ideas wearing a very, very clever disguise. All they're waiting for is for someone to find the right key. So what other unsolvable riddles are just waiting to be unlocked?